Okay, let's continue on this second lecture with by inspecting the case where what we have on the right hand side is a constant load that appears at time equal to 0. So usually, to be really mathematically precise, we should write it like this, right? Where the function ut is like this, right? Is the step function. This is time, meaning that when you multiply ut times anything, you just cancel the negative times, right? And you leave the positive times the same. So basically we have a system that at time t equal to 0 receives a load equal to P0, and before times equal to 0 there was no load, right? Okay, so in addressing the solution for this thing, let's refresh our, well, not refresh, but refer to the previous lecture and make the following point. The homogeneous solution, that is the solution to the single degree of freedom equation when the right hand side is equal to 0, can be written as this, that is e to the minus psi omega t, which is the decaying function, times, now instead of putting initial conditions here, we can say that in general it is simply equal to C1 times the cosine of omega damn t plus C2 times, now why do I want to do it in cosine and sine? Is that how I had, it doesn't really matter. Sine of omega damn t, it doesn't matter the order, of course. Okay, so that is the homogeneous solution. Now, let's get back to this equation. So if I want to find the solution of a differential equation, second order, in which the right hand side is not equal to 0, then we begin by looking for what we call the particular solution, that is a solution that when substituted on the left side will equal the right side, right? So let's postulate that a particular solution is equal. Now, one procedure, remember, to do the postulating the form is that you take the right hand side plus all its possible derivatives. In this case, the right hand side is just a constant. All its possible derivatives are 0. So we just simply say that the right hand side, that the postulated particular solution is just a constant. That means that one derivative and two derivatives of the particular solution are 0, and then we simply have that k times the constant d, and I'm not going to write the u0, the step p0, it's understood, it's just p0, right? So I have that the constant d then is simply p0 over k. Now that's obviously the static solution, right? If I have a load P0 and I apply it to a static system, I just get P0 over K. And it's quite clear that I can take the solution Qt equals to P0 over K, and that will satisfy the equation, right? Because if I put two derivatives is 0, one derivative is 0, and then K times P0 over K is P0. So the reason why that is not the total solution is because that solution does not satisfy the boundary conditions. For example, if we look at time t equal to 0, right? If we look at time t equal to 0, this solution would say that the response, that the displacement is P0 over K. But we may know that the system is actually starting from rest. So at time t equal to 0, the displacement must be 0 if it's starting from rest. It could be starting from somewhere else, right? But if it's starting from rest, then the initial condition for displacement is 0, and so, so it would be for velocity. So the way that we correct the edge issue or the boundary condition of the particular solution is by adding the homogeneous solution and then solving for the constants. So in this case, we would say that the total solution, right, which is the homogeneous plus the particular, is equal to e to the minus the damping omega t, which is the decay, multiplied times some constant times the cosine of omega damp t plus some constant times the sine of omega damped t plus the particular solution, which was P0 over K, right? Again, I will erase in order to give myself some room. But for a step load, this is the generic solution. The constant C1 and C2 will depend on whether the system is starting from rest or from some other condition. So let's look at the particular case where the system starts from rest. Okay? So if the system starts from rest, then that means simply that Q0 is 0, no displacement, and Q0 dot is also 0. Okay? So it's just a matter of substituting here. Now I got here the expression for displacement. I'm going to write it here a little bit smaller. Q sub t is equal to e to the minus psi omega t, and then the parenthesis C1 cosine of omega damped t plus C2 sine of omega damped t. That is plus P0 over K, and then I'm going to write in under it the derivative. So the velocity in general is equal to minus C times omega e to minus C omega t, and when I go like this, that simply means that parenthesis over there, plus e to the minus C omega t times the derivative of this, which is obviously omega damped common factor of, and I can put the parentheses, this one doesn't change sign, so this would be C2 cosine of omega damped t, and this one would be minus C1 sine of omega damped t, right? And so we have the expression for the displacement and the expression for the velocity in the instant where the single degree of freedom system is subjected to a step load that appears suddenly in time at time equal to 0. Now, if we consider the case where it starts from rest, we have to equate these two things to 0. So from the first equation, we have that 0 is equal to a time t equal to 0. This is going to be 1. This is going to be C1, right? This is going to be 0 plus P0 over K, which immediately tells us that C1 is minus P0 over K, right? All right. Now to get the second constant, we come to our second equation, and we say if the velocity is 0, time t equal to 0, this would be 1. That's minus the damping times omega. This parenthesis will be C1. Excuse me. This parenthesis will be C1, right? No C2. And what is plus P0 over K, right? No, wait a minute. Did I do something wrong? Yeah. Sorry, my head shifted from here to here. Start again. This was the first equation. Now I'm going to do the second equation. So 0 is minus psi omega. This is a 1. The parenthesis is C1, right? And that's it for the parentheses, just C1. Now I come to this term here, which is plus, this is a 1 at 0, so that's omega damped. And the second thing here is C2, and this is a 0 here, right? So we have something like that. Now that means that from this expression, we have that C2 is equal to, this goes positive, omega psi times C1 divided by omega damped, right? That would be C2, but we already have C1 is equal to this, therefore we have that C2 is negative P0 over K times the damping times omega over omega damped, okay? All right, so it looks like we've got our constants C1 and C2 And so our complete solution is this expression here, in which we substitute these two things, right? So I'm going to write them here for my own reference. C1 is minus P0 over K, and C2 is equal to minus P0 over K times the damping ratio times omega over omega damped. So that allows me to erase here and to go here and simply rewrite it now. So we have Qt equals e to the minus the fraction of critical damping times T. Open this bracket. C1 is minus P0 over K cosine of omega damped T. C2 is minus P0 over K times the damping ratio times omega over omega damped times the sine of omega damped T. Close this thing plus P0 over K. Okay, so that's the solution, and I guess we can write it again a little cleaner by writing P0 over K, common factor of, I'll start from over here, 1, and then this looks like a minus, so minus, and then I'm going to open a parenthesis. This part here looks like cosine of omega damped T plus, and then this would be the damping ratio times omega over omega damped times the sine of omega damped T. We close this, close the bracket, and I believe that's everything, right? So I will erase everything except that. And this is what we have, right? So this is the response of the system that starts from rest and gets subjected to a step load. It is of interest to take a look at the undamped case. So if the fraction of critical damping is 0, then we have the particular expression P0 over K, parentheses 1, and then if the damping is 0, this term falls out, and when the damping is 0, omega damped is the same as omega, so we have minus cosine of omega t. And so this one is an equation that is simple enough that we normally just remember it. It's the static solution times 1 minus cosine omega t, which tells us, now how big can this be? If you look at cosine, right, cosine varies from minus 1 to 1. And as time passes, this goes through all the values from minus 1 to 1. So the maximum response is going to be when this is minus 1, right? Every time it's minus 1, this goes to 2, and you get a response which is 2p0 over k, which means that the dynamic response, right, becomes at some points twice of the static response. So the system is like this, right? You have a load P0, and P0 over K is here. Okay? If the problem was a static problem, we would say if I apply a load to the structure deforms P0 over K, of a single degree of freedom, of course. Now, in reality, at time t equal to 0, this is 1, right? And 1 minus 1 is 0. And therefore, we already agreed that we're starting at 0. So if we apply the load as a blast suddenly, then the response will actually start at 0. Cosine omega t is 1, and then as the time increases, you get a little bit less than 1, right? And so you get 1 minus something. you know, 1 minus 0.99, 1 minus 0.98, 1 minus 0.9, etc. And so the response starts to grow. At some point it goes through this, and at some point it becomes twice as big. And it's doing this, where this value here, right, this is P0 over K, and this is 2P0 over K. So the response goes from the static value, okay, to twice the static value, and then to 0, and then like this, right? We would say that there is a dynamic amplification, if you want, of 2, in the sense that at the time of maximum response, the response is 2 times what you would gotten if you had applied the load slowly, or very slowly, right? If you apply the load very slowly, you get P0 over K. If you apply the load as a blast, you get 2P0 over K. Now, if the structure had some damping, instead of the response being which is, if the structure had some damping, we would get the solution that we've already written and I erased. But as you can imagine, what would happen is that you would not reach exactly 2, right? You would reach less than 2. You would reach something that is less than 0, I mean more than 0, and then a little bit less again, and then a little bit less here, and then a little bit less there. And if you have damping, eventually the response will go to the static solution, because the behavior that produces this vibration is the homogeneous part, which has the e to the minus psi omega t in front, which dies with time. From a physical point of view, it's just not, it's very obvious, right? I mean, you have the mass here, and you have a damper, and you apply this thing as a blast load P0 that appears suddenly, and the system takes off, and eventually starts going from, this is the static position, it goes to twice that and to 0, and it's vibrating like this, right? And if it has damping, it'll go, and then it'll eventually stop here, at the position that it would have been statically. One thing that is worth noting is, although I'm not going to show it here, but we might do it in class maybe when we meet, just to illustrate that this difference here, when you have damping, is actually quite small, so that the maximum response of the system to a blast with damping or without, without damping is 2 times. But with damping is not that different from 2 times unless the damping is very, very large. So for all practical purposes, the second peak and the third peak, as the peaks go up, the response is, obviously, the peak response is decaying. But if your system design is governed by the maximum response, then the maximum response would occur on the first cycle, and is actually going to be pretty close to 2 for reasonable values of the excitation. Okay? For reasonable values of the damping. Now, it's clear that we could do the same thing for different loads, and we could use all kinds of different loads that are of interest. For example, we could say generically, right? It would be like repeating, but we have a mass, we have a stiffness, we have a dashpot, and we have a load PT, right? And in all cases, the total response is the homogeneous response plus the particular solution. And we have now obtained a particular solution to the step load, which we found that it was simply P0 over K, right? Like that. The homogeneous solution is, in all cases, e to the minus psi omega t, C1 cosine omega damp t, plus C2 sine omega damp t. And you must find the constants C1 and C2 to satisfy the initial conditions after you add the particular solution to the homogeneous, right? Now, what kinds of loads on this side could we derive things? Well, we could derive it for various things, right? They're all going to be just more or less the same thing, go through the motions. But, I mean, I'm going to conclude today and to conclude lecture 2, just to get one more practice, I'm just going to do the case in which the load is like this, right? So it reaches a certain value. Let's just say that this is alpha, and this is 1. So that this is the load, and this is time. So this is going up, has the equation alpha t, okay? And this is t. And at time t, let's say Tp, the load stops. So this here is just alpha Tp, okay? This maximum load. We could do that one, or we can do that one. And then the other one that is of interest, for which we will, this one is really not that important, but I'm going to do it just for a little bit more practice. But in the following lecture, next time, we are going to look at the solution for a harmonic load. Now, a harmonic load may be a sine or a cosine, or more in general, it's like a sign that begins, you know, shifted. So let's say this is harmonic. So in the harmonic loading, there is a certain period, which is the time that it takes this thing to repeat itself. And this period, we're going to say that it is 2 pi over this omega, this capital omega. So we're going to refer to this omega as being the frequency of the loading, okay? Frequency of the harmonic loading. So, in summary, we know the homogeneous solution. We've derived the particular solution for a step, and we have 2 more particular solutions to deriving the class before we go into looking at other ways to do this thing for arbitrary p. But in our immediate future, we have to solve the problem where the loading is a linear load that stops, and this one is a harmonic load that has a particular frequency and, of course, a particular amplitude, which we could call it whatever. You know, we could call it Q or something, the high value. Okay? I didn't mean to put that this was necessarily Q. I meant to say this could be starting anywhere, so this could be maybe like, you know, like that, I guess. Okay? So let me do this to conclude the lecture today. So if we have that the load is of this form, it's going up alpha for every unit of time, it stops at Tp here. This is f of t or p of t, whatever we want to call it. This is t. So what we have is mq double dot plus cq dot plus kq is equal to u of t, because the load really doesn't go into the negative direction, times alpha t, right? So it's the slope of the load. And u of t, of course, is again the step function, right? Heaviside function. So we divide by m and we get q double dot plus 2 omega times the critical damping ratio times q dot plus omega squared times q is equal to alpha divided by m times t. And I've taken the u out for convenience in notation. So now we have, just like before, Q as having a homogeneous and a particular solution, and we're looking for the particular solution. And for the particular solution, what do? We take the right-hand side plus all its possible derivatives. So in this case, I'm going to say the right-hand side is either, could be d0 or it could be d1t, right? So it's either a constant or this. So the second derivative is 0, the first derivative is d1, and so we get 2 omega fraction of critical damping times d1 plus omega squared times this thing, which is d0 plus d1t, right? And then that's equal to alpha mt. So from this side we get 2 omega psi d1 plus omega squared d0, okay, is 0, and omega squared d1 is alpha over m, right? Why is that? Because of course the right-hand side here is a linear function of time, so the coefficient of the time on this side is omega squared d1, so I have to equate it to alpha over m. And the part of here that is constant, 2 omega psi d1 plus omega squared d0, there is no constant on this side, so I make it equal to 0, right? So from here we have that d1 is equal to alpha over m omega squared, and we realize that since omega squared is k over m, then this is just simply alpha over k, where the m's cancel out. And then from this equation here, we find that d0 is equal to minus 2 omega times the damping times d1 divided by what? By omega squared, right? And so we have that d0 is equal to minus 2 times the damping times d1 divided by omega. Cancel 1 and cancel 1. And that's minus 2 times the damping ratio. Now we have that d1 is alpha over k, right? And then we have omega. So that's my d0, and I can say then, I'm going to erase here, again to clear things in my mind. So I'm just going to say that the particular solution as a function of time is equal to d0, which is minus 2 damping alpha k omega. That's d0, and then d1 we have alpha over k and then times t, right? Or perhaps we can write that a little bit nicer by taking the alpha over k common factor of t minus 2 times the damping divided by omega, right? Now that solution, of course, that particular solution is valid provided that 0 is less than or equal to t, t is less than or equal to tp, right? Because after that the load is gone, right? Okay, so that's our particular solution. If I didn't make a mistake, I mean I make lots of mistakes, so it's possible that I have an error, but you know, assuming there's no error, that is the particular solution. And then we would simply say the total solution is the homogeneous for the particular plus the particular, so we have this thing proceeding the same as always, C1 cosine of omega damp t plus C2 sine of omega damp t. And then we have to add the particular, which is plus alpha over k times t minus 2 times the ratio of critical damping over omega, right? For 0 less than t, t less than tp. And then Given that condition, we would calculate our constants routinely by imposing the initial conditions. So for example, if system is at rest, doesn't have to be, right? We could say in any particular problem, the system is starting at, I don't know, whatever, right? 2 inches. And starting instead of 0, it's whatever the value is. But if the system is at rest, we would say 0. Well, actually, I have to do the derivative as always. So before I do that, before I say this, let me just put the expression for the derivative once more. So we have minus psi omega t e, no, not omega t, minus psi, differentiating with respect to time, minus omega psi e to the minus psi omega t, the parentheses, right, plus e to the minus psi omega t, take the derivative of the parentheses, which once again is omega damped, open the parentheses, this one gives me C2 cosine of omega damped t, and this one gives me minus C1 times the sine of omega damped t, right? Same as always, same as before. And that is this part, and then I take the derivative of this, which is plus alpha over k, right? Then we would say if the system is at rest, if at rest at t equal to 0, then we would have 0 equals, right, 1, C1, 0, minus 2 ratio critical damping over omega times alpha over k, from where it follows that C1 is equal to 2 ratio critical damping alpha divided by omega divided by k. Again, assuming I have no error. Even if I do, you can see what the procedure is. And so 2 psi over omega k. And then on the second one, we would say, okay, so with velocities, we would say 0 is equal to minus omega times the damping. That's a 1. The parenthesis becomes C1, right? That's 0. And then we have, again, I keep looking, okay, and then I keep looking at this now. That was the parentheses. Then this is 1 plus omega damped, and then times C2, right? Plus, wait, I think I made an error here. Yeah, when I put alpha over k, I had to say minus alpha over k. No, that's correct. Plus alpha over k, yeah. The second term was a constant, disappeared, so plus alpha over k. So I have C2 omega damped, this is 0, plus alpha over k, right? And so we find that from here, the C1, so I can put this on this side and find that is 2 psi alpha divided by omega k times omega times the fraction of critical damping equals, I'm sorry, minus alpha over k, put that one on this side, is equal to omega damped C2, right, I think. So this one came to this side, C1 was 2 psi alpha over omega k times omega psi came here, minus omega over k equals omega damped C2, right? And then I'm going to erase here because I get confused with so much stuff on there. I got C1 already in there. And so from here we would have C2 equals, 1 over omega damped. I'm not going to try to simplify it right now because it doesn't matter. 2 fraction of critical damping alpha psi, this omega cancels with that one, divided by k minus alpha over k, and that's it, right? So that's C2. And so I already had C1 before, and so substituting C2 over here and substituting C1 over here, that would be the complete solution, right? For the problem where the load is starting like this. And it stops at Tp. So for 0 less than T, T less than Tp, right? Now, let's conclude with this little, not symbolic, but just conceptual experiment or discussion. Let's say that the load that we had was this. Right? Let's say that the load that we had was this. And we want to know, just for this discussion, just to bring the point, let's say I want to know what is happening at this time. So let's say this point is TA, this point is TB, and this point is TC. So it is clear that I can say that this loading is equal, because we're talking about a linear system, right? So I could say this loading is equal to this, let's say this value here was N1 and this value here was N2. So I could say that it is equal to N1 up to here plus something that goes like this, which is N2 minus N1, right? That'll give me this part, plus something that begins here at N2 and goes to TB, like that, right? Let's see. Well, yes, I could do it like that, but maybe that requires a little bit more explanation. Well, I don't know. I guess what I'm trying to tell you is that if I want to find the solution at this time, then you can simply say, okay, I calculate the response due to a step which I already know, and I evaluate it at time TA. So I get the step, evaluate at TA, right? And then I have free vibration after TA up to here. That accounts for this part, right? What are the initial conditions here? Whatever the response due to N1 is at time TA. Now I have this, which I already also have the solution, in which this is N2 minus N1. I go in, I find the response at this place, right? It's over, that gives me the initial conditions. I get the free vibration of that at this time. Then I start here. Now it's not necessarily obvious right now what the solution for this one is, but it is. It's a combination of two things. Anyway, I do this, I find the response at this point, I evaluate the initial conditions here, and I get the free vibration of this up to here, and so the solution of this plus this is the answer for this load at this point, right? So you can combine free vibration at this point. I mean, you can combine anything you want because it's a linear problem, but at this point we have the solution for a step. Let's say we have the solution for something like this, and we have free vibration, right? In closed form. Okay, so I will call it done for lecture 2 here, and then we'll start lecture 3 by introducing convolution.